In this video, we will use the modern atomic theory as well as the subatomic particles that were introduced in previous videos to describe the difference on the subatomic level between the various elements, what we mean by isotopes, as well as ions. For this discussion, it will be helpful for you to have a periodic table close at hand. As a reminder, under modern atomic theory, atoms can be broken up into three subatomic particles. All atoms are comprised of these same three subatomic particles: protons, neutrons, and electrons. The protons and neutrons are found to have nearly identical masses, listed in this table below, and the electron itself has a significantly lower mass. This means that the vast majority of the mass of any atom is coming from the protons and neutrons, which are found in the nucleus. The charge on an electron and proton are equal in magnitude but opposite in size. You can see here the charge on a proton and the charge on an electron. Elements themselves are defined by the number of protons. The most important number to the identity of an atom is the number of protons in the nucleus. The number of protons defines the element that you will be working with. The number of protons in an atom's nucleus is its atomic number. Looking at your periodic table, typically the atomic number will be found directly above the chemical symbol. So for the case of something like carbon here, which we'll be using a lot in chemistry, the chemical symbol is C, and the atomic number for carbon is 6. For nitrogen, the chemical symbol is N, and the atomic number is 7. The atomic number corresponds to the number of protons for that element. So all carbon will have 6 protons. All nitrogen will have 7 protons. The symbol that we will be using for the atomic number will be Z. An easy way to distinguish the atomic number from another number that you will commonly see on the periodic table, which is the atomic mass, is that the atomic number is an integer value, meaning it is 1, 2, 3, 4, 5. There's no decimal places, whereas the atomic mass will have a decimal value. So for example, hydrogen, which has an atomic number of 1, has a mass of 1.00794 AMU. Isotopes are atoms that have the same number of protons but different number of neutrons. Again, the number of protons dictates which element we're working with, but the number of neutrons does not change the element type. So you can have a particular element with multiple different types of isotopes. Because of this, there is a need for a shorthand representation for conveying the information of which type of isotope we're working with. Not only the type of element, but also the number of neutrons. There is a common representation shown here below that gives all the information that one would need for a particular atom. It comprises 4 different values, although often the charge is left out if the charge is 0. In the upper left corner, you have A, which is the mass number. The sum of the number of neutrons and protons in an atom is its mass number and will be represented by the symbol A. So again, A is the number of protons, which have a positive charge, plus the number of neutrons. The atomic number, which we recently saw, is what defines the type of element that you're working with, and that will be equal to the number of protons. This X will be the chemical symbol, which can be found on the periodic table, and then this C here is the charge. The charge is the relative number of protons versus electrons. Now, because electrons have a negative charge, if you have an extra electron, one extra electron would give you a -1 for the charge because you have one extra subatomic particle with a negative charge. If, however, you have one fewer electron than you have protons, you would have a charge of +1. A 0 means you have the same number of protons and electrons. Again, remember that the charge on a proton and the charge on an electron are the same in magnitude but opposite in sign. And atoms themselves, atoms and molecules, don't generally interact with an electromagnetic field. So most atoms, when you come across them, are going to have a 0 charge, though not always. A charge indicates that you have either added extra electrons or pulled electrons off. Adding or removing protons and neutrons is much more difficult and is typically only done through nuclear means. X is the chemical symbol, A is the mass number, Z is the atomic number, and C is the charge. An isotope is essentially the same element that has a different number of neutrons. So all atoms of a given element have the exact same number of protons. However, they do not necessarily have the same number of neutrons. As an example, all neon atoms will contain 10 protons, but there are several different isotopes. One isotope contains 10 neutrons, another one contains 11 neutrons, and the third one contains 12 neutrons. In all cases, there are a limited number of isotopes that you will find for a given element. In this case, all three types of neon atoms exist, and each in slightly different masses. The way we would represent these in terms of our previous shorthand notation is as follows. The isotope that has 10 neutrons we would represent like this. The 10 down here on the bottom left represents the number of protons, and you can see that each neon has that exact same value. Our value up here, the A, right, which is our mass number, is the number of neutrons plus the number of protons. So because it's neon, it has 10 protons, or you could think of it, because it has 10 protons, it's neon. So neon has 10 protons. The superscript, or the number in the upper left in our mass number location of 20 means that it has 20 minus 10, so the number here, 20, minus the 10 for the protons, gives you 10 for the neutrons. In this example here, our neon 21, it has 10 protons, and then up here, it would be 21 minus 10 gives you 11 neutrons. Here, for neon 22, because it's neon, it has 10 protons, and again, the number in the upper left, where our mass number is the number of protons plus neutrons, so we have 22 minus the 10 protons gives us 12 neutrons for this isotope. Atoms with the same number of protons but a different number of neutrons are called isotopes. There is another type of isotopic representation that gets used a lot, and part of the reason for that is the Z value, our number of protons that is typically in the bottom left, is a bit redundant once you have the chemical symbol. So for example, neon, all neon has 10 protons. So writing the 10 in the bottom left is redundant once you say that it is neon. So another way of representing isotopes is with the chemical formula, is with the chemical symbol followed by the mass number, as written here. So you have your chemical symbol dash your mass number. So you could have Ne20, Ne21, Ne22, or sometimes it's written with the chemical name, neon 20, neon 21, neon 22. This provides all the same information as the previous set, indicating the number of protons. Because it's neon, it has 10. And then the 20 here gives us the mass number. So from this, we can figure out the number of protons and the number of neutrons. Neon has 10 protons because it is neon 20. 20 minus 10 is 10. So this particular isotope of neon will have 10 neutrons as well as 10 protons. In our example here, neon 21, because it's neon, it has 10 protons The 21 here is our mass number, which is the number of neutrons plus the number of protons. So we would take 21 minus 10 for the number of protons, because it's neon, gives us 11 neutrons. So this isotope here for our neon has 11 neutrons and 10 protons. Now, just because an element has multiple different isotopes does not mean that those isotopes have the same abundance. In the case of our neon, neon 20, neon 21, and neon 22, the vast majority of it comes in the form of neon 20. About 90% will be found in the form neon 20. About 9.25% is in the form of neon 22, and only 0.27% is in the form of neon 21. The relative amount of each different isotope in a naturally occurring sample of a given element is roughly constant. They do change over time, but for the most part they are fairly consistent. The percentages are called the natural abundance of the isotopes. Up until now, most of the discussion of our isotopes have focused on the number of protons and neutrons, but there is our third subatomic particle, the number of electrons. The number of electrons in a neutral atom is equal to the number of protons in its nucleus, and this will be designated by its atomic number Z, which in our shorthand representation is found in the bottom left. In a lot of chemical changes, however, atoms can lose or gain electrons and become charged particles, which we will call ions. Positively charged ions are called cations. A lot of metals are going to be forming cations. So like sodium ions will typically form sodium plus. Negatively charged ions are called anions. Most of the time you'll find that the non-metals, which we will get into where these are located in future videos. So the non-metal elements form anions. An example of this would be our fluoride ion, F-. You can denote the relative number of electrons compared to the protons by the charge in the upper left. So, for example, our sodium has a plus, which means that it has more protons than it has electrons. Again, keeping in mind that electrons have a -1 charge. So the reason that this has a positive charge is because it has lost one of its negative charge carrying subatomic particles, the electron. So this is Na plus because it is missing an electron. On the other hand, this F- has an extra electron, right? F-, this negative here indicates that you have an extra negatively charged subatomic particle on this particular element. Let's now go through a couple examples of going back and forth between our numbers of protons, neutrons, and electrons and our shorthand representation. So, example 1. What is the atomic number, mass number, and symbol of the chlorine isotope with 18 neutrons? So first thing we need to do is find chlorine on our periodic table. It is located here. So chlorine has 17 protons. Its atomic number is located right there, 17. So protons are equal to 17. This is not saying anything about it having a charge, being an anion or cation, so the number of electrons would also equal 17. Okay, so writing out our symbol, the atomic symbol for chlorine is Cl, shown here in our periodic table. The number on the bottom left, our Z value, is the number of protons, so that is 17. And then our value that goes in the upper left, our mass number, A, is equal to the number of protons plus the number of neutrons. So that would be 17 protons plus 18 neutrons for a total of 35. And because it doesn't say anything about this being a cation or an anion or some sort of an ion, our value in our upper right here, stays a 0, and so we leave it out. Okay, let's move on to the next part. How many protons, electrons, and neutrons are present in an atom of chromium 2+, and we have our numbers here. So the number of protons is our value that is in the bottom left of our symbolic representation, so right here. So our number of protons will be 24. Our number of neutrons would be our value, our mass number in the upper left, so that would be 52 minus our number of protons, 24, which will give us 28. Our number of electrons is going to be our 24 value, our number of protons. And because we have a +2 charge, we have 2 extra protons, or we have 2 protons more than we have electrons, which means we have lost 2 electrons. Again, remember that the electrons have a -1 charge each, so in order to get this +2, we had to lose 2 electrons. So we will have a total of 22 electrons. For our next example, let's look at something similar, but a couple different examples. What is the atomic number, mass number, and symbol of carbon isotope with 8 neutrons? Well, carbon is located here on our periodic table. And so the symbol is going to be AC. The atomic number is listed in the value directly above our symbol, which is a 6. So our atomic number, which is Z, is going to be equal to 6. Right? Our mass number, A, which again is equal to the number of protons plus the number of neutrons, will be equal to our neutron number, 8, plus our Z value, 6. So 6 plus 8 is equal to 14. So our shorthand symbol would be carbon 14. This is in itself a way of representing it. Or we could also add our 6 in the bottom left. Again, because this doesn't say anything about it being a cation or an anion, our charge, which sometimes appears in the upper right, would be 0, and for this reason we leave it out. Looking at our second example, how many protons, electrons, and neutrons are present in an atom of 197 with an atomic number of 79, an unknown symbol with a +1 charge? So we want to know all that information as well as identify what X is. So for this, our atomic number is 79, and so we just have to find that on our periodic table. Looking down here, here is atom 79, Au, which is gold. So answering the last question first, what is X? X is Au, which is gold. Okay, so what we would have in terms of writing this out would be 197, 79, Au plus. That would be how we would write it out. Okay, going back to the first part of the question, how many protons, electrons, and neutrons? Well, we have our number of protons is equal to our atomic number, so that would be 79. Our number of electrons would be equal to our 79 minus 1. And the reason it's minus 1 is because we have a plus here. So we have 1 extra proton, or we have 1 more proton than we have electron. So this would be 79 minus 1 to give us that +1 charge. So that would be equal to 78. And then the number of neutrons, right, would be equal to our mass number, 197, minus 79, which would give us 118. So from this, you can see that you can go back and forth between your atomic number, mass number, symbol, number of neutrons, and the shorthand representation.